So our fourth chapter is the three-dimensional structure of proteins. In our last chapter, what we talked about were individual amino acids. We were talking about the proteinogenic amino acids and how those different R groups, first of all, how you can classify them, what they look like, and maybe one of the more important things is what types of interactions can take place between them based on their classification. In addition to that, how do those different groups change based on a solution's pH? All of that is very important on the individual molecule level, so looking at one of those amino acids, but it's also important in the scope of the overall three-dimensional polymer that is, or of a protein. So unlike most organic polymers, protein molecules adopt a specific three-dimensional conformation. So based on the difference in amino acid sequence, they're going to adopt a different conformation. This structure is able to fulfill a specific biological function. This structure is often called and commonly known as the native fold. The native fold has a large number of favorable interactions within the protein that kind of stabilize it, and there's an entropy cost to folding the protein into one specific native fold. So what that last item, or that last bullet point, is talking about is going from that newly synthesized polymer, so that long chain of amino acids, how does it go from there into this ultimate kind of globular type of structure that it adopts as its kind of final state? So what are the favorable interactions? In the last chapter, one of the things that I really highlight and really focus on are I talk about ionic interactions based on cationic and anionic amino acid R groups. But we have to remember all of the different interactions that can exist within a protein. First of all, you do have hydrophobic residues, and as a result, the hydrophobic effect is going to be in effect and does have an impact on a protein's fold. There are hydrogen bonds that exist between the N-termini and the C-termini of different amino acid groups. So the N-termini of one amino acid is going to interact with and form a hydrogen bond with the C-termini of another amino acid. London dispersion forces. These are medium-range weak attractions between atoms that contribute significantly to the stability of the interior of the protein. That's one of the very important parts of this, the interior. Then you have your electrostatic interactions. These are long-range, strong interactions between permanently charged groups. So salt bridges, especially those buried within the hydrophobic environment, strongly stabilize those proteins. So for all of these different groups, or for all these different types of interactions, I want you to kind of think about what are the potential residues involved. So hydrogen bonds, well, we know with hydrogen bonds we've got the N-termini and C-termini of different amino acids, but we also have the R groups that are capable, or several R groups that are capable of hydrogen bonding. Your electrostatic interactions, you should be thinking about a aspartic acid or a glutamic acid. A group that's going to be negatively charged working as an anion, it's going to attract a cation. So you could have like an aspartic acid over here and a lysine over here. This lysine is positively charged, this aspartic acid is negatively charged. The strong interactions between those two amino acid R groups are going to help stabilize the overall structure of that protein. So this is kind of a simplistic view of it, but we'll unpack this a little bit. So there are 4 levels of protein structure, cleverly titled and cleverly named the primary, secondary, tertiary, and quaternary structure. Now, with this, we should think about the different types of interactions and bonds that are going to stabilize these. Your primary structure, that is just the sequence going from the N-termini to the C-termini. What are the amino acids and what is the order of those amino acids? Your secondary structure, and this right here highlights a alpha helix. That is one example of a secondary structural element. Now, secondary structure is going to be stabilized by what are commonly known as backbone interactions. Now those backbone interactions, CTIONs, those are going to be the hydrogen bonds of the N and C termini of different residues. Okay, now what that means is that the secondary structure has virtually nothing to do with different R groups. And I say virtually nothing to do because I don't want to say that it has absolutely nothing to do, and I know I said virtually, but the R groups, the different amino acid R groups, are not particularly relevant to the formation of the secondary structure. Tertiary structure, on the other hand, well, your tertiary structure is going to largely be stabilized by the R group interactions. So when we think about hydrophobic residues kind of being forced together and cations and anions interacting with one another, or interacting with an ion or a dissolved ion or something like that, you should be thinking about your tertiary structure. There can be hydrogen bonding in the tertiary structure, but again, it's hydrogen bonding between the R groups, or R group and N termini, whereas your secondary structure, that is interactions that are solely the backbone. So the N termini and C termini, they interact with one another, secondary structure. If one of them interacts with an R group, then you're talking about tertiary structural stability. Your quaternary structure is basically the same, but it's a little bit more complicated. I'm going to draw a little line right here, and it's not extremely important, but what I want you to think about is that there are some proteins that whenever they fold as that one unit, as that one polypeptide chain, that is their final state. Their native fold is that one polypeptide unit that has folded into 3 dimensions. There are other proteins, and what's the example that's used here is hemoglobin. Now, hemoglobin is a protein that is multiple polypeptide chains that have folded together to make one large entity. So think about it like if you got, actually here's my, let's see, just a second. So let's think about this. This is a polypeptide chain. It folds up, and there you go. There's our 3-dimensional, our tertiary structure for blue proteinase. Okay. Now, there are some proteins that they will achieve this one polypeptide chain folded in 3 dimensions. They are happy as a clam. Now, there are other proteins, these 2 proteins. These 2 proteins are different from that other one in that they're going to form a quaternary structure. So their overall final shape is when 2 polypeptides fold in 3 dimensions and reach some final shape. So what is stabilizing this and what is stabilizing this? Well, it's largely going to be R group interactions that are going to stabilize this, and it's R group interactions that are going to stabilize this. The difference between your tertiary structure and your quaternary structure is these are R group interactions, when I'm talking about my quaternary structure, R group interactions between 2 different polypeptides. Tertiary structure, R groups between one, or R groups all on the same polypeptide chain. So when you think about something in its 3D shape, well, this is in its 3D shape. This too is in its 3D shape. The difference is how many polypeptides are here. Tertiary structure is just 1 polypeptide. Quaternary structure is 2 or more polypeptides. So the primary structure, as we already kind of talked about, the primary structure is stabilized by the peptide bond. That is just the primary structure is just the sequence of the amino acids from the N termini to the C termini. What is going to stabilize that? Are peptide bonds. The structure of the protein is partially dictated by the properties of the peptide bond. The peptide bond is a resonance hybrid of 2 canonical structures. The resonance causes the peptide bonds to be less reactive compared with esters, as an example, and it causes it to be quite rigid and virtually planar. Now, to exhibit a large dipole moment in favor of the transconfiguration is one of the aspects of that peptide bond. So here is the peptide bond that we're accustomed to. Now, what I'd like you to do is be sure that you can orient yourself with what are the different, like, where is my R group? And if you wanted to find out where your R group is, all that you'd have to do is identify your alpha carbon. Here's an alpha carbon, here's another alpha carbon. Now, if I wanted to go ahead and fill this in a little bit more, what I'd say is here's my N termini and here's my C termini. But we didn't show all that because what we wanted to see here are what are the atoms that are present or relevant to my peptide bond. Well, the ones that are the most important are this carbonyl oxygen, the carbonyl carbon, the amino nitrogen, and the hydrogen on that amino group. Now we have resonance stabilization with that, where we can go on to ultimately have a -1 charge on our oxygen and a +1 charge on our nitrogen, or a carbocation with that positive charge on our carbon and a -1 charge on our oxygen. Now, as is the case with resonance structure, we're not really concerned with those two charges because they're basically mitigated or stabilized with the help of that resonance. Now, the rigid peptide plane has partially free rotations. So what you need to think about with respect to those rotations and with respect to that peptide bond is, I'm just going to move all this text over a little bit. Sorry about that. There we go. The rotation about the peptide bond is not permitted due to that stabilization, due to that resonance structure. Now, we have rotation around bonds connected to the alpha carbon, and those are the phi and psi angles. And so what this phi angle is the angle around the alpha carbon, the amide nitrogen, or sorry, it's around the alpha carbon amide nitrogen bond. Okay, our psi angle is the alpha carbon to the carbonyl carbon bond. In a fully extended polypeptide, both phi and psi are 180 degrees. So what we saw on the previous slide, that would be 180 degrees. The organization around the peptide bond paired with the identity of the R groups determines the secondary structure of that protein. So that's one thing that I'd like to talk about. Previously, I used the phrase stabilized. So the secondary structure is stabilized by the hydrogen bonding, however, of the N and C termini. However, it is influenced. It is certainly influenced by identity of R groups. So that's one thing to keep in mind and keep track of there. So here's another representation of a peptide, or a polypeptide. We've got our different R groups. Like I said, whenever you're talking about, and actually this is a good figure because it shows us our amino termini, and it just goes on. We're not concerned with the end, where it actually begins. And likewise, we're not concerned with where it actually ends. We just want to know, looking at a profile, what are we seeing here? So I'll draw your attention to this 1, 2, and 3 alpha carbons. Now these 3 different alpha carbons, we've got our R groups in different kind of directions. This first alpha carbon right here, where I've drawn that little blob, that has my R group coming out of the page. My second alpha carbon right here has my R group going into the page. And my third has my alpha carbon coming out of the page. Now, whenever we talk about protein structure, one of the most important things is what does it look like in 3 dimensions? And in order for something to have an appearance in 3 dimensions, it's got to have some kind of flexibility and mobility. Now, one thing that I just kind of went over was that peptide bond itself is very rigid, and that's because of the resonance stabilization. So we're not going to have any rotation between this C and this N. That peptide bond right here, it's not going to rotate. However, our phi angle and our psi angle, that's where we can have rotation. So think about it like you have a series of sheets of paper, basically. And on those sheets of paper, you have those different, at each of those different sheets of paper, you have different atoms. So this one plane right here, this second plane, third plane, fourth plane, these are going to rotate, but they're going to remain in the same plane. They're going to rotate because of the phi and psi angle. Now, it's a little bit weird to think about because well, I don't know, I just think that it's kind of complicated and challenging to think about and visualize that, but that's what we have going on. We have these two adjacent planes that we can't have any wiggle room of that plane, so we're not going to have this oxygen right here. That oxygen's not going to move forward or backward or anything like that, but instead this whole plane will rotate, and it will rotate only because of the phi angle. It can also rotate because of the psi angle, but yeah, so it's kind of challenging to wrap your mind around there. But what I need you guys to know, what I want you to think about is all of the atoms within a peptide bond are in the exact same plane. You have rotations about two different bonds, the phi and the psi. Which one is the phi? The phi bond is the one going from a N termini to an alpha carbon. The psi angle, or the psi bond, is going from an alpha carbon to the C termini. We have no rotation about that peptide bond, it's just about the phi and the psi angles.